new pedigree. She married twice here. Okay. What do we got? Yep.
Did she marry again?
She married again. She married twice. She didn't have any offspring the second time. But that happens. You have to be able to draw it in the pedigree. You know, she's entitled, right? Okay. So she got married again, no offspring from this marriage. That's a legal symbol. You guys think that's funny? It's real, you know? Okay, I mean, it doesn't mean she's married to two people at the same time, right? This is not a temporal picture. So what do we got here? Yep.
Do we assume that, I mean, do we have to look at the children to determine the type of the marriage in the family?
Of this person?
Yeah, we aren't told to assume that they can be that they're only, they don't fit the
Well, I'm drawing them as an empty circle, empty symbol here, indicating that we do not think they have the trait. They're not carriers. How do you propose to find that out? Look at the children. Well, the children are affected. They could be carriers. You know, the data are what they are. You got to interpret them. Does this person have to be a carrier? What kind of a transmission do you think, what kind of trait do you think this is? Dominant? Does this look like autosomal dominant to you? What? Yep.
Because not all of the kids have that trait.
Oh, not all the kids have the trait in the first generation. And if this was dominant, they'd all have it? What's a possible genotype for this person? Mutant over plus. And these kids could be mutant over plus. This could be plus over plus. And this could be plus over plus, mutant over plus, plus over plus, mutant over plus, and plus over plus. It would be one possibility. On average, what fraction of the kids should get the trait? About half the kids, right? So let's see what characteristics we have here. We see the trait in every generation. On average, half the kids get the trait. Half of the offspring of an affected individual are affected. What else? Males and females, roughly equal in males and females. Sorry? Two male, 1, 2, 3, 4, 5 to 2. So it's a 5 to 2 ratio? Oh, in the offspring, it's a 2 to 1 ratio. So this is like Mendel. You see this number and you say, okay, 2 to 1. Is that trying to tell me something? Not with 6 offspring. That's the problem, is with 6 offspring, 2 to 1 might be trying to tell you 1 to 1. And it is. If I had a dominantly inherited trait where there's a 50-50 chance of each offspring getting the disease, and it was autosomal, not sex-linked, there'd be very good odds of getting 2 males and 1 female. Because it happens. Flip coins. And it happens. So you have to take that into account. And here you see that See, what else we got? Roughly equal numbers of males and females. They transmit equally. And unaffecteds never transmit. This would be the classic autosomal dominant trait. Right? Here, this mutant would go mutant over plus, mutant over plus, plus over plus, mutant over plus, plus over plus, plus over plus. And you'd see here that 3 out of the 5 here, and 1, 2, 3 out of the 6 there. That's a little more than half, but it's small numbers here, right? This is a classic autosomal dominant, as in the textbooks. Yes?
Wouldn't it still be likely that the males have a higher likelihood because there isn't so many things that are coded on the Y chromosome?
Turns out not to make too much of a difference. Turns out that there's lots of genome that's on neither. And so it is true that males are more susceptible to certain genetic diseases. So there'll be some excess, but it won't matter for this. Now, in real life, it doesn't always work so beautifully. We'll take an example, colon cancer. There are particular autosomal dominant mutations here that cause a high risk of colon cancer. People who have mutations in a certain gene, MLH1, have about a 70% risk of getting colon cancer in their life. But notice it's not 100%. You might have incomplete penetrance. Incomplete penetrance means not everybody who gets the genotype gets the phenotype. Not all people with the M over plus genotype show the phenotype. Once you do that, it messes up our picture colossally. Because tell me, how do we know that this person over here is not actually M over plus? Maybe they're cryptic. They haven't shown the phenotype. And maybe it'll appear in the next generation. That'll screw up everything. It screws up our rule about not transmitting through an unaffected. It screws up the rule about not being shown in every generation. And it will even screw up our 50-50 ratio. Because if half the offspring get M over plus, but only 70% of that half show the phenotype, then only 35% of the offspring will show the phenotype. Unfortunately, this is real life. When human geneticists really look at traits, many mutations, most, except the most severe, are incompletely penetrant. And so you have to really begin to gather a lot of data to demonstrate that you're dealing with an autosomal dominant trait that's incompletely penetrant. And then there are other issues. There's a gene on chromosome number 17 called BRCA1, mutations in which predispose to a very high risk of breast cancer, but only in women. Males carry the mutation and do not have breast cancer. There are other mutations that do cause breast cancer in males. Males have breast tissue and can have breast cancer, but the one on chromosome 17 does not. And so there you would only see this transmitted through females. It would skip into males without showing a phenotype, et cetera. So in real life, life's a bit more complicated. All right, so autosomal dominance. Now let's take one more pedigree. Sorry? Sex limited, but not sex linked. It's on chromosome 17, which is a bona fide autosome, but it's sex limited in that phenotype can only show itself in an individual who happens to be female. Yes?
I like autosomal recessive.
Sorry? Oh, you like, how come autosomal recessive?
Yeah, it should be like the same ratio, but if that the left one is M plus.
So if that left guy up there is actually a heterozygote, and up there, that individual, so if we had a homozygote, heterozygote, homozygote, woo! You can interpret that pedigree if you want to as an autosomal recessive, provided that M is pretty frequent in the population. That's right. Human geneticists, in fact, to really prove that they've got the right model, collect a lot of pedigrees and run a computer model. The computer model first tries out autosomal recessive, tries out autosomal dominant, tries out dominant with incomplete penetrance, and for every possible model, figures out the statistical probability that you would see such data under that model. And when the data become overwhelming, and you say, yeah, with one pedigree, any pedigree I draw on the board, it could actually fit almost any of the models. It doesn't say this in the textbooks, but it's true. I get enough pedigrees, and eventually I say the odds are 10 to the 5th times more likely that this collection of pedigrees would arise from autosomal dominant inheritance with incomplete penetrance of about 80% than from autosomal recessive inheritance. Then I get to write a paper about it. That's really what human geneticists do, is they have to collect enough. Now, any other organism, you'd just set up a cross. But you can't. And as long as we have non-trivial models, we really have to collect a lot of data.